So mass spectrometry is a really robust, highly utilized technique. Actually, mass spectrometry is interesting because it can kind of be considered both a separation technique and a detection technique built in one. But we often couple it. Where you see mass spec is usually coupled on the back end of some sort of front end separation technique. So that might be a GC, a gas chromatography MS, GCMS would be the GC on the front end to do separation of gases, and then the mass spectrometer on the back end to do detection, or HPLC-MS, so you have a mass spec detecting on the back end of an HPLC, etc. I'll talk a little bit about why one could actually consider it as a separation technique, and people use it as a separation technique based on mass, but that's probably not its most common utilization. So mass spectrometry really in a broad sense is the field for the study of the mass of atoms or ions or molecules or fragments of molecules. And by molecules we can mean anything from like the size of like a hydrogen atom all the way up to nowadays with really more advanced techniques we can study full intact multi-unit proteins like a ribosome, all with mass spectrometry where we're literally weighing or measuring the mass of these objects in space. The product of a mass spectral analysis is a mass spectrum, and they look very different depending on what you're trying to weigh and what you're trying to measure. In this case, this is a mass spectrum of a small compound that I have here, from a GCMS, from a gas chromatography mass spectrometry system. So mass specs come in a variety of flavors, from really, really simple, robust, sort of workhorse machines that we call quadrupoles, all the way up to high resolution cyclotron measurements and everywhere in between. And really they're constructed for different purposes depending on the level of accuracy and precision, but also the type of analyte that you're trying to measure. Are you trying to measure small molecules or fragments of small molecules? Are you trying to measure really, really subtly different isotopes of heavy metals? Or are you trying to measure giant proteins or protein units that are fully assembled without perturbing their quaternary structure? There's a mass spectrometer for all of them. I'm going to walk you through a few different flavors, but the general main three components, certainly this is not exhaustive, there's going to be exceptions, but the general three components for most mass spectrometers are: one, that it has an ion source; two, that it has a mass analyzer; and three, that it has a detector. I want to walk you through each of these main principles, and I'm going to do that by walking you through sort of the classical original mass spectrometer, which is this fixed magnetic field, what's sometimes known as a magnetic sector mass spectrometer. So the first thing in the system that is actually shown here, actually in the exploded view diagram, so you can sort of follow this out. This is our ion source in this magnetic sector instrument. And almost all mass spectrometers will have some version of an ion source, and that's because of the way that mass spectrometers, or the actual mass analyzer part of mass spectrometers, work. So the vast majority of mass spectrometers out there utilize a mixture of magnetic and electric fields to preferentially sort or filter certain atoms or ions or molecules or fragments of those, but they have to be charged in order for the mass analyzer to work, which means that if we have neutral molecules coming into the system, which is what we have here, these little oblong shapes, they have to pass through in some way. They have to get into an ion form. And even more, most ion guns also, or ion sources, have some sort of responsibility in getting the molecules into a gaseous state. So here I guess we're sort of assuming these neutral molecules are already gaseous, which means they're sort of far apart and there's no solvent. But some ion sources are also responsible. As we get, and we'll talk later about some of the modern ion sources for big molecules like proteins and peptides, and how the ion source is really coupled both from an ionization perspective, but also getting the molecules into a gas phase state in a gentle way, so we don't destroy or break apart the superstructure of the molecule. In this really simple sense, the simplest possible ion source for mass spectrometers, what's been around forever, is this thing called an electron gun. And literally what happens is you fire an electron beam at a very specific energy across a gap, and then your neutral molecules pass through that beam, and in doing so, it's sort of like ballistics, right? Not all your molecules are actually going to get struck. It's sort of a probabilistic thing, and the ones that do get struck may not get struck by or absorb all of the energy, but many times what will happen is that beam is strong enough to sever most bonds, especially carbon-carbon and carbon-hydrogen bonds. And so what you'll get is a fracturing of a molecule, and you'll get the expulsion of an electron, which will render your molecules or the fragments of your molecules in a positive state. And that will allow then, if you have your ions now in a positive state, that'll allow them to interact with some sort of magnetic or electrostatic fields to parse out different things based on mass. So our mass analyzer in this case, and actually before I do that, let me show you a quick animation of that. All right, so I'm going to show you electron ionization, so it's just the simplest form of ionization. This is coming from a video. I'm playing this back kind of fast, but I'll pause it along the way. So you've got your sample coming in here. It's being vaporized, so it's in the gaseous state, comes in through this inlet, and then there's a filament, and that filament here is biased at a certain voltage relative to this plate that's down here. And so there's a large electrostatic potential that's being dropped across this region. This entire box here is being pumped out. So there's virtually no air in there, very little air in there. So this is under vacuum. And so this filament, it could be like a tungsten filament like you'd see in an incandescent bulb. A large amount of current is passed through here such that it starts to heat up ohmically. And at some point, if this thing is hot enough and there's enough energy in the electrons inside of this, and it's biased such that this is negative and this plate down here is positive, you can get what's called thermionic emission. And those negative electrons will have just enough energy to be ionized off of the tungsten filament, and they'll be drawn straight down to this positive plate down here. So you've got your molecule. The neutral molecule is that yellow dot in the center, and that collides, and it's going to pop an electron off down to this trap electrode, this anode down here. It's the positive electrode. And then there's some sort of other electronic optics in here which will guide the ions through the system. It's not really sending out waves like that, but it is biased positive relative to this ring over here. And so what that does is it creates a repulsion, and under a certain bias you can get your ions to then flow through here. Again, this whole thing is pumped out, so it's under vacuum, so you don't have to worry about collisions with other extraneous molecules that would otherwise be in here. And that's an important part about mass spectrometers, that it doesn't necessarily, I didn't list it as a component, but it really is an honorary fourth component, because virtually all mass spectrometers in some way have some part of the system that's under vacuum. And so vacuum pumps are integral to the functionality of most mass spectrometers. So up close, we can look at this cartoon, and it'll show us what's happening via ionization. So it depends on what you're putting in the path, right? So if you put like a chlorine atom in the path, then it may just pop an electron out of its outer valence and render it positive. Or if you've got a larger like alkyl chain like pentane here, ionization can cause that thing to ionize, but then that ionized form of that alkyl chain is not super stable, right? You've got this weird sort of carbocation situation going on that's not stable on a linear chain like this, especially a terminal chain. And so what it starts to do is undergo some pretty interesting gas phase chemistry because that carbocation is no longer stable. And so it starts to collapse and fall apart into various fragments. What's interesting about molecules is that as long as our electron ionization step is consistent, meaning as long as we're applying the same energy into our electron ionization step, which is standard, typically it's 70 electron volts, then what we get is a pattern of abundances of various fragments of the original molecule that's unfragmented. And from this, we can deduce what the original molecule was, and we can compare across systems, because as long as everybody is smashing apart their molecules in the same way, then they get nominally the same pattern. And so this is generally how electron ionization will occur. So back to this picture, once you have your original neutral molecules into a positive state, and maybe you have also some fragments in this system, then it's the task of the mass analyzer to come in and actually separate those things out. So the goal here is to get all of our neutral molecules into some charged state, and then in the case of like gas chromatography, mass spectrometry, we actually want to break apart the molecules into individual fragments, and then we're going to allow all those charged fragments to pass through a magnetic field. In this magnetic sector instrument, it's really simple. You have essentially a giant magnet, like an actual chunk of iron, magnet that's not variable, so we can't change its overall field. It's static and fixed. But what happens then is if this vacuum tube with the ions passes through this magnet, this bore, then what we get is a differential interaction of our fragments or our ions with that field. And really what we're separating based on now is both mass of that ion and its charge. And we call that the mass to charge ratio of our ion. So in this case, lighter ions are less affected by the field, and they take a trajectory that's a little high on the path, and then these other ions down here are sort of perfect, the blue ones, and then the heavier ions down here have a trajectory, they collide with this tube. And of course, we can then augment the path of this tube. You know, there's several different ways practically we could do this. So what you can essentially do then is collect light ions, measure how many you have there, and then sort of move through all the way to heavy ions, and that gives you the full spectrum, something that would look like this, where you have light mass to charge fragments or ions or whatever they are up to the heavier stuff by simply moving your detector relative to the path of these ions as they move through the tube. This is the most simple mass analyzer, so I'll introduce you to a couple more here. But before we get there, we're really just talking about the general layout of the three components. The third component, of course, then is the detector, because we can do all the separation in the world. And by the way, the reason why I started this video saying that mass spectrometers can kind of be considered a combination of separation device and a detector is that a mass analyzer really is a separation tool based on mass. But normally we think of separating whole molecules first, then putting them in a mass spectrum, and then the mass analyzer is separating based on, say, the fragment size. But that's not always true. Sometimes in like a magnetic sector instrument like this, you might be separating a bunch of isotopes of, say, lead, of all the different stable isotopes that exist, in which case you're not separating fragments, you're literally separating your analytes inside the mass analyzer. In that case, it becomes both a separation tool, and then we need something on the back end to actually measure how many of each of those ions we had, and that's no different here. The most common type of detector that we have for these systems is this thing called an electron multiplier. These things are ubiquitous. They're really, really common. Sometimes people call these squirrel cages. The way they work is you have ions in, and then you have a series of electrodes that are called dinodes that are biased at angles such that you get ballistic transfer of these ions and then subsequent electrons that get ionized off of each of these metal electrodes. So an ion comes in and it dislodges an electron here, and we get some electrons that come flying off the cathode, and then the next dynode is biased positive relative to this first one, more positive, and so those electrons come flying down further. This one's biased even more positive, so on and so forth. And so you start with, you know, hypothetically a single ion that strikes the first cathode, and as it cascades through the chain of dinodes, it gets amplified such that when it hits the final plate over here, this should say anode, this is measured Usually we measure the current here, and then we convert that current into a voltage, and that scales. But this can give us roughly, 10 to the 5th, 10 to the 6th sort of amplification from our original ion. So one ion maybe gives us 1,000,000 electrons, and we measure that as current. That's how many instrument detectors work. Of course, there's 1,000,000 different versions of this, and the electronics all change. But this sort of cascading effect is a pretty common one because it has built-in amplification.